Energy. Let's look at the metabolism of glucose. Okay, glucose has the formula C6H12O6. It's a solid. And so if you eat sugar, it's sugar. It's one of the sugars. It's not table sugar. Table sugar is glucose and fructose put together. But if you take glucose and breathe in O2 gas, then what we're going to generate is CO2 with the exhale. We'll also generate water, and we'll generate some energy as well. So how much energy is generated? Well, it depends on how much glucose is metabolized. So if we can metabolize 1 mole of glucose, 1 mole of glucose will require 6 moles of O2, generate 6 moles of CO2, 6 moles of H2O. In metabolism, this occurs over many steps, but this is the end of the net reaction here that occurs. So the amount of energy is going to be 2805 kilojoules per mole. And so we can write that in here, 2805 kilojoules. This is kilojoules per mole of glucose written, so we just write it kilojoules because that's how many moles of glucose we have being metabolized. But if we look at this, the efficiency, this is just off the University of Florida, the efficiency of glucose metabolism is only 39%. That is 39% of the energy here is going to be converted into what we call work, where we can power things. 61% is converted into heat. And so 39% of the glucose we're going to use to do things with. And so there's 39% efficiency. Meaning this, 39% of the energy can be used to do work. The remaining 61% we aren't going to use. The remaining 61% is lost as heat. Although it's not really lost because heat is important. We'll just say lost as heat in quotation marks here. And so let's take a look at a problem. Maybe let's look at, I'm going to go to here.
Excuse me. 39% work, what is that?
61%? 61% will be converted into heat. And so only so if you have 100 calories, you can only use 39 out of 100 because the remaining 61 calories are used to be heat. So we can take a look at there's a problem here, sorry. Well, anyway, I'll just make up a problem here. Let's say you want to climb a mountain, this. And so how much energy does it take to climb? Well, the minimum amount of energy it takes to climb is if somebody tied a rope around you and pulled you up like this, rather than taking some long route out. And so the minimum amount, you have to do work against gravity. And work against gravity is given as mgh. And so this is from physics. You can ignore this if you'd like. But depends on how high you climb. The higher you climb, right, the more work.
Also, it depends on the mass. The greater the mass, the more work. And so it comes out of physics that, the minimum amount of work that's going to be required is mgh. That's where m is the mass, g is the gravity. You're fighting gravity here. It's much easier to go downhill than uphill. And h is the height. But that's the minimum. So if somebody put a pulley around you, a rope and a pulley, and lifted you up this, then it's different in air. But if you're going to have to climb this, then we're going to guesstimate it's going to take, what do you think, twice as much, 3 times as much, 4 times as much? Let's just guess. Guess it's going to take 4 times the minimum. So this is the minimum amount here. So it'll take 4 times as much. And so how high do you want to make this climb here? We make it 1,000 meters? 1,000 meter climb? Like 3,000 feet? Okay. Or how high? Let's go with 1,000 meters. Okay. And so this little bit of physics is just to talk about energy and the units of energy here. Now, okay, let's say this is 1,000 meters, so about 3,000 feet. 1,000 meters. And so what we're doing is we're going to guess it's going to take 4 times the minimum. And so 4 times and mgh is the minimum. Because it's probably going to take some circuitous route up the mountain. And so this is going to be the energy required to climb the mountain. Okay, so that's 4 times the mass. Okay, how heavy should this person be? In kilograms. 52 kilograms. 52 kilograms is the mass of the person. Times g. G is a constant. It's 9.8. In physics, you memorize this. Does anybody know what the 3 sig figs, what g is? Funny thing is, I don't think I ever memorized it, 3 sig figs. This is in newtons. I don't want to write newtons. Okay. We'll just go with 9.8. 9.81. Actually, 9.81. 9.8, 9.8, 9.8. Oh, 9.8 is okay, but we'd like to go with one more than what's given. So 52. 9.81. The units are interesting for this. The units are going to be kilograms, meters squared per second squared. Oh, actually, what am I doing? It's not. Sorry, that's not G. This is meters per second squared. I'm getting ahead of myself here. And so G is given in the units. It's kind of weird units. It's acceleration, meters per second squared. And then we have H. H is 1,000 meters. So, so let's go ahead and calculate this. See what it comes out to here. And so I'm going to get 4 times 52 times 9.81 times 1,000. This 4, I'm adding it. This 4 is a guess. We're guessing it's going to take 4 times. so what do we get here? I get,
Million.
2,040,480. The units are gonna be kilograms. Meters times a meter is a meter squared per second squared. Now, this kilogram meter squared per second squared is defined as the joule. It's the joule of energy. And so it's probably best to convert this into kilojoules. What we're going to need is we're going to need 2,040 kilojoules for this climb. 2,040 kilojoules required. All right, 2,040 kilojoules required for that climb. Where are we going to get that? Well, we're going to get that from glucose metabolism, food. And so let's figure out, well, how many calories is that? Well, actually, let's do this. We're going to figure out how many grams of glucose is required. We're going to have to assume 39% efficiency, because the heat is not going to raise you up the mountain. It's the work that's going to get you up the mountain. And so how many calories is this? Well, as we recall, a joule is 4.184, so 4.184, I'll just divide that. This is going to come out to 487,686 kilocalories, or 487.6 food calories. So about 500 food calories. All right, so we had that equation with the glucose. So what we can do is this. How many grams of glucose is required? We're going to assume 30% efficiency. And so what we want is we need 2,040 kilojoules needed. And so what we're going to call that is this. Now, what does 39% efficiency mean?
61?
Well, yeah, it could be 61% loss, or it could be this. It's 39 out of 100. What? It's not grams. Well, it could be grams as well. We could do grams, but it's in terms of energy, so it's better to do it in terms of energy. Grams and energy are going to be directly proportional. If you double the number of grams, you're going to double the number of calories. You're going to double the number, if you eat 10 grams of sugar versus 20 grams. 20 grams of sugar is going to have twice as much energy, but we're talking about not the grams. We're talking about the energy yield. Now, if this is energy yield, that means we're going to get 39 kilojoules of work for every 100 kilojoules produced. And so, in other words, we can think of this 39 as the actual yield, out of 100 kilojoules. This would be our theoretical yield here, in that sense. And so, is this actual or is this theoretical, Is that going to be the total energy, or is that going to just be the... No, this is the amount we actually need to climb the mountain. And so we have to have this much energy. And so this is what we're going to call the actual yield. That means we need to produce more energy because we're going to lose 61% of that energy to heat and not be able to do any work with that. Right? And so in this case, this means this. That means we're going to have for every 39 kilojoules that we have as our actual, we're going to have to produce 100 kilojoules in theory. That way a lot of the kilojoules of energy are gonna be kind of wasted, quote unquote, as heat. Now, okay, then we know that for every 1 mole of glucose, C6H12O6, we're going to get, what was it, 2850? 2805 from here. And so for every 1 mole of glucose, we're going to produce 2805 kilojoules. And so when you metabolize 1 mole of glucose, it's going to produce a total amount of energy of 2805 kilojoules. However, not all that energy will be used. 61% will be used as heat, 39% will be used to climb the mountain. Does that make sense? No? Yes? Doesn't make sense at all? Okay. Well, we'll do one more calculation here. So we got to figure out how much does glucose weigh. Well, glucose weighs 180.2 grams per mole. So this is 180. Sorry, let me double check this. $180.18 is what I usually calculate based on rounding. We'll do 180.16. All right, so let's go ahead and do the calculation here. So it's 2040 times 100 divided by 39 divided by 2805 times 180.16. 335 grams. 335.96 grams of glucose. Okay, what if we didn't? Okay, what if there's, okay, this is 39% efficiency. What if there's 100% efficiency? That is, for every kilojoule of energy produced by the metabolism of glucose, all that energy could be used. And so the equation would be different. We need 2,040 kilojoules. And so for every 1 mole of glucose produced, we get 2,805 kilojoules worth of energy for every 1 mole. This is something that somebody's determined, you know. They look at the efficiency, we call this respiration. We look at the efficiency of respiration, that is metabolizing glucose. The total energy is 2805 kilojoules. So somebody figured that out. Then times 180.16 grams per mole of glucose. And so let's see what that number comes out to. So 2040 divided by 280. Not 280, 2805. Divided by 2040 divided by 2805 times 180. 131. 131.0 grams of glucose. We're only allowed 2 6/5. Subscript 5 here. Subscript 1. All right, so basically this if I could use all that glucose to generate energy to climb that mountain, I'd only need 131 grams of glucose. But since 61% of that energy is lost as heat, I have to consume a lot more glucose because of that. So this is the factor. Actually, did I, you know what, maybe I didn't get this far. Did I talk about energy?
Yeah.
Did I talk about delta H, endothermic and exothermic? Yeah, yesterday? Okay, I just want to make sure.
No, you didn't. No, you didn't.
I didn't talk about endothermic and exothermic?
You mentioned it like
negative.
Negative.
Oh, just
yeah.
Okay, you know what, in the afternoon I got a little bit farther, I think, so I actually did a problem. Is this the first problem I did with energy? Did we do another problem in the book?
You were going over
31?
pretty much.
But we didn't finish it? All right, let me talk about that one first, because that's why. Maybe I jumped too far ahead with this. This is using percentage in stoichiometry. Well, this is the one I did in the afternoon, 63, but I didn't do that one yet, correct? No, okay, let's do 63. Make it. Okay, let's take a look. Number 63, quicklime. The common name for calcium oxide is made by heating limestone, calcium carbonate, in slowly rotating kilns, which are a type of oven. This is a very interesting reaction. There's a documentary, I think it was like Discovery Channel documentary. It's on Netflix, but it talks about Roman architecture, how this reaction here was critical in them inventing concrete and stuff. Pretty interesting. And so anyway, this is an endothermic or exothermic reaction? It's going to consume 178 kilojoules. And they're talking about, well, Romans had access to coal, which can generate the high temperatures needed for this particular reaction to take place. So what quantity of energy in kilojoules is required to decompose 5.80 kilograms of limestone? And so what we do is we use this just like a conversion factor. So this is 1, this is 178, this is 1, this is 1. And so we'll just use it as a ratio, just like everything else. And so what we want to do is we want to decompose 5.80 kilograms of limestone. Limestone's calcium carbonate. And so what we'll do here is we're going to convert from kilograms to grams. And so the kilograms cancel, that gives us grams of calcium carbonate. And then we've got to go to moles. Stoichiometry, the heart of the math is moles. So calcium is it 40.08, or is it?
40.07.
Okay, we'll just round it to 40.08. Carbon is a 1201. And 3 oxygens is going to be 48.00. It's 9010. 610. 100.09. So there's 100.09 grams of calcium carbonate per mole. So we get rid of the grams of calcium, and we're left with moles. Okay, now we've got moles, now we can enter that into the stoichiometry here. And so we see there's 178 kilojoules for every mole of calcium carbonate. So we can cancel out the moles. So for every mole of calcium carbonate, we require 178 kilojoules. If we had 2 moles of calcium carbonate, it'd be double that. 3 moles of calcium carbonate, it'd be triple that. So this is just a stoichiometric factor like anything else, and so we can figure out how many kilojoules are required here. So let's go ahead and calculate it. It's going to be 5.8. Well, times 1,000. 5.8 times 1,000 divided by 100. 0.09 times 178. This is going to give me 10,314.7 kilojoules. So in other words, I'm going to need, well, how many sweet pigs? I got 3 sweet pigs. So we'll just do 10.3 times 10 to the third kilojoules. We're going to need a lot of energy. It's the same as the foot count. Okay, that's endothermic. Let's look at an exothermic reaction. Let's try number 65. The quicklime produced in question 63 is frequently converted to calcium hydroxide, sometimes called slate limes. Let's take a look at the previous reaction. The previous reaction, what kind of reaction does that look like to you? Does this look like an acid base? Acid base, or what does it look like to you? Redox or metathesis? Well, metathesis is ion combination. So are we combining ions? And if so, what ions are we combining? Yeah, this is a decomposition, and this is called an acid base. This is a Lewis acid base type reaction. It's hard to see here, but this is not an element plus element decomposition type thing. And so that's an example of Lewis acid base reaction. This is also an example of a Lewis acid base reaction. This one, some people will say this is a combination reaction, but it's not like a combination reaction where we're taking carbon plus oxygen and making CO2. This is quite a bit different. This is a Lewis acid base reaction. And so this is exothermic. So what mass in grams of quicklime was processed in a reaction that transferred 291 kilojoules of energy? Why don't you do this problem here on your own and see what you get?